Okay, so generally speaking in physics, we have two types of measurements, two major families of measurements that we group things into. We have vectors and we have scalars. Okay, a vector is a measurement that includes both magnitude and direction. What is magnitude? What is magnitude? Size, right? Magnitude is talking about size. It's how big something is, right? So vector includes both the size of something and direction. So when we classify things as vectors and scalars, there's a much smaller category of things that are vectors than scalars. Okay? A scalar is simply a measurement that includes magnitude but not direction. And I don't know what this is doing here. I don't know where that came from, honestly. So just get rid of it. Okay, so scalar is a measurement that includes magnitude but not direction. So our first two examples of scalars and vectors are distance and displacement. So a distance is a measurement of how far an object has traveled, where displacement is a measurement of where an object is relative to some point at the end of a trip. Okay? So if an object begins at point A here, and it moves like this to point B, and I want to talk about the distance it traveled, what do I need to include? Yeah.
Like the package from A to B.
Okay, so like all this dotted line stuff counts, right? If I'm talking about the distance from A to B, that I actually traveled, right? What if I'm talking about the displacement?
It's just from A to B.
Okay, so I should draw a line from A to B, right? And I shouldn't just draw a line. In fact, it should be as short as possible line, but it shouldn't just be a line either. It's a straight line, yes, but it should be an arrow because it should include direction. And the arrow actually indicates the direction from A to B, right? And you'll notice there is only one displacement from A to B, right? There's no other displacement possible from A to B because by definition it represents the shortest possible length between the 2 points, right? The straight line between the 2 points from one to the other. Okay. So we have Joe and Ted, and they're starting from the same point, and they walk two different paths, and they end at the same point. So how does the distance traveled by the two men compare? And how do their displacements compare to one another? Such a shame. Okay, what do you think? Compare the distance traveled by Joe and Ted. Some people ask me why they're not Bill and Ted. Very silly people would ask those questions. Yes, what?
Well, the displacements are the same, but the distance traveled is different.
Okay, so the distances traveled are different, but the displacements are the same. So are the displacements the same in terms of direction or magnitude? Both? Okay. So can two objects have the same magnitude of displacement but different directions?
Yes.
Okay. Right? That's obvious. So two objects can begin at the same place. Both travel 5 meters, but one goes north and one goes east. Right? Same magnitude, different directions. Can two objects have the same direction of displacement but different magnitudes? Of course they can. Two objects go north, one goes 10 meters, one goes 2. Right? Same direction, different magnitudes. Can two objects start and end in the same place and have different displacements? They can't. By definition, that's what displacement means. It's a straight line measurement from start to finish, right? Can two objects have the same displacement but start and end in the same place? Yes, they can. Right? something could start here. I mean, the same magnitude and direction. Right? Something starting at here and go like that, right? And it's the same direction, same magnitude, but they start and end in the same place. Two parallel lines would have the same magnitude and direction of displacement, don't have to start and end in the same place. Okay. So let's get a little more specific. Let's figure out the distance traveled by 10. All right, I'm gonna need a ruler for that. I'm gonna break out my ruler. You guys should have a ruler, right? Unless you don't have the notes with you today, in which case, don't. Say you're really nice to see this. These are the notes destined for someone who's these are notes that are meant for a fully remote student now. Oh, you need okay, so let's measure it up. All right. So what do you think? How far did Ted travel? 26.8. I got 8. Okay, hold on. Now I have to actually do it next. So you guys get similar answers? I got 24.2. You get 24.4. How about you? 26.6. 24.2. What's that? He got 24.2. All the smart people get 24.2. What did you get? 24.4. 24.6. Okay. I'm not sure why you guys can't measure stuff, right? It's a simple operation, right? You take the measurements, put the ruler, and you read the number, right? And then you add them, and then you multiply by 2, right? So, like, what's the, why, I got 24.4 or 2, or, why are you, I don't get it. What's the problem here? Do we have a problem? So the contention here is that it's perfectly fine for us to have slightly different answers, right? Okay. So what we're dealing with here is something called, and I'm going to use the board to write on. You guys don't have to write this stuff down. This is what we call statistical error. Okay. Statistical error are small random variations that occur when you take measurements, right? I measure something and I say, oh, it's 2.7. You measure it, you say 2.6. He measures it, he says 2.5. I measure it again, I say 2.8, right? And which one of those measurements is correct? Which one of those 5 measurements that I took is correct? The one that I took, the one that you took, the one that he took? Which one's right? They're all right. That sucks. Okay, so they're all right? Because we're allowed to have small random statistical variations in our measurements, okay? So that's normal. Statistical variation is normal. So the other type of error is systematic error. And guys, I gotta tell you, if you don't perk up and get involved, this is gonna be a really boring slog of a class, right? If it's just me and him, you're not gonna like it around here, okay? You need to start speaking up and getting involved. Systematic error would be something like, okay, I calculate that it's 24.2, but I tell you guys it's 242. Then I calculate something else that's supposed to be 30, and I say it's 300. I calculate something else supposed to be 48, and I say it's 480. Every single time I made the same mistake, right? I did some conversion error, or I made some measurement error, but I did it the same way every time, right? Every time I made the same mistake. Systematic errors are correctable. Okay? You can correct systematic errors. And if I can figure out what the mistake is, I can correct it and I can get all my correct measurements and data back, right? Right. Statistical errors, by contrast, can't do anything about it, right? You can't stop it. The only thing you can do is minimize it. And ironically, do you know how you minimize statistical error? It's kind of ironic how you do it. You measure a lot. Like you just keep taking measurements, right? You keep taking more and more and more, and eventually you get a solid average, right? That's how you minimize statistical variation, by taking lots of measurements. Okay, so when I say statistical error, here's the problem. Most of you are thinking of something else that you've been taught to cite as a source of error. What is it that you're thinking of when I say statistical error? Human error, right? And to me, human error doesn't exist in a science class, right? Because when you say human error to me, I think this. Human error is a mistake, right? A human error is a blunder, right? And science has no room for human errors, because to avoid human errors, we take multiple measurements to make sure we're measuring it correctly. We have multiple people looking at what we're doing to make sure we don't make mistakes, right? So if you were to say in a lab report or an AP question, well, we didn't get the right answer, or the answer is wrong because, or it's off because of human error, that's not good. You don't want to say that, because what you're essentially saying is it's not right because I did what? I did something wrong. I made a mistake. That's not what you're saying, right? The correct way to say it would be, well, it's a little bit off, but it's within the boundaries of, okay, statistical error, right? within the boundaries of statistical error. It's the variation that we would expect to see, okay? So that's the difference, okay? So try to stay away from using the term human error and start talking about statistical error, right? You'll encounter systematic errors from time to time, but when it happens, like if you're doing an experiment or something, if you get to the point where you're doing experiments, and I see some sort of statistical error, systematic error happening, more often than not, I'll tell you, oh wait, you're multiplying by the wrong thing, or you're taking the wrong measurement or something, right? But that's like correctable stuff that we can work on right away. Okay. Okay, so we got that the distance Ted goes is around 24.2 meters. And Joe, this is like 11 meters, right? Something like that? Okay, perfect. Now, if we're talking about Joe's displacement, right, we really have to include what? Direction, perfect, right? So, but see, here's the thing. If you're actually drawing arrows on paper, the direction is right there. You don't have to describe it, right? It's there. There it is. There's the direction. I don't have to say any more than that. However, if you were forced to describe it, right? If you had to give a description of the displacement here, you would need some reference, right? So you might like have to define north, south, east, and west, and then you'd use some angular measurement to describe it. And we'll talk about that in some more detail later. Okay, next example. You're starting from city A. Car drives 250 miles due east to city B, such and such to city C, and then city D, and whatever, right? Stay. So, it's kind of lost, right? City A, B, C, D, F. There's a lot of words there. Anyone got any suggestions? Draw a diagram. She's a genius. Now, why do I say she's genius? Because in this physics class, you're going to constantly be drawing diagrams, right? You want to always draw diagrams of things anytime you can, because it will help you understand the scenario better. Okay, so I'm going to draw a diagram. Perfect. So city A, and then I'm going to go 250 miles due east to city B, and then 300 miles to city C, and then 700 miles to city D down there. Okay. Perfect diagram, right? You seem very miffed. What's the problem? You don't like my diagram? You got something against my diagram? Okay, so what? So what now? What? Huh?
Should you draw the arrow or should you orient the diagram?
You know what? I can fix all this for you. You don't like it? You still don't like it?
The displacement would be like how much?
Well, no. I mean, it makes sense.
No,
What you're saying makes sense. Yeah.
It's just not the easiest way to understand.
It's not the easiest, right? Is there anything wrong with what I drew?
No, it's just not.
No, but it's dumb. It's dumb. Like, I would never draw the picture like that if I were actually doing this for myself. Like, if I read this problem, I would draw the picture like this, like you did, hopefully. Right? You probably drew. Go away. You probably said, okay, I got city A, and you want me to go east, 250 to city B. Then you want me to go 300 to C, and then you want me to go 700 to D. Someone in an earlier class is like, shouldn't you draw it to scale? I was like, well, if you want to draw it to scale, knock yourself out. Does drawing it to scale really make any difference? Does it not having it to scale impede my understanding of what's happening? Not really, right? So there's nothing wrong with drawing it to scale, but there's really no need. It's just a sketch, right? It's a sketch to help you understand quickly. You should definitely have this second arrow be longer than the first one, but this last one is kind of like, who cares, right? What's the difference? Okay, so, yeah, I mean, absolutely. I would draw the diagram oriented left to right, like this, because I, in my brain, think east that way, just like everybody else. But I drew it the other way just to illustrate the point that it's not wrong. You can do it that way. If you want to make your life harder, go ahead. But there's really nothing wrong with it.
If you do it that way, do you have to specify like which?
You're probably better. You're probably better. In fact, if you draw any diagram like this that requires a north, south, east, west, you're probably best off doing one of those. And in fact, if it's a test or something, it may already have one of those little north things defined so that you know which way you're supposed to draw things. But you could generally expect north to be oriented toward the top of your page if it's appropriate. Okay? So what's the distance traveled by this car? 1,250 miles. Perfect. What's its displacement from its point of origin?
750 miles west.
Okay. Notice you included direction. Okay. So let me ask you this. Would it make any kind of sense, instead of writing 750 miles west, what if I did this? Minus 750 miles. Would that make any kind of sense? Okay, that's true, but I'm talking about displacement.
It kind of makes sense because you're going in the opposite direction than you started in.
Okay, well, hold on a second. In order for that negative 750 miles to make sense, what would I have to have done before I wrote it? Okay, and something else. Okay, I have to choose something. You're taking point A as a 0 point, as the origin. That's fine. But you're kind of defining this, yes?
Negative 750 miles east.
Nope. I don't have to add an east to it if I do this.
You have to define the positive direction.
I have to decide which direction is positive and which direction is negative. And she's falling into the normal, okay, well, if A is the origin, then to the right of the origin is which way? Positive, and to the left of the origin is negative, right? So we're saying, we're making the decision. If we do this, right? And again, I am not saying that this is the right way to do it. If you had asked me this question, the best answer, honestly, is 750 miles west. Why? Because everything in the question is already defined in terms of east and west, right? But I'm just proposing another way to report it that might be useful in future applications, right? Because you can pick a one-dimensional axis and say one direction is positive, the other is negative, and that axis could be lined up along any direction. It could be northeast and southwest. It could be north and south. It could be up and down, right? So if we define a one-dimensional axis, if we just pick one way to be positive, the other way is negative, that would make perfect sense if we did it.
How would you indicate what's positive?
Okay. Well, in this particular case, if you wanted to do it, you would probably want to set up something and say, east is positive. You will commonly see this in multiple choice type questions, especially when you're graphing things. They'll be like, okay, an object is heading east and this is happening or whatever, and on the graph it says, take east as the positive direction. They do it all the time, right? They define it in advance so that when they present you with choices and they give you positive choices and negative choices, you see what I'm going with that, right? They define what the positive direction is, then they present you with positive and negative choices for your answers, okay? Another way you might want to do this, and this is really kind of out there and going ahead quite a bit, but we could call this minus 750 miles I hat, Now this I hat thing is what we call unit vector notation. Okay, so in unit vector notation, we define an I axis or an I unit vector in the positive x direction, a j unit vector in the positive y direction, and there's a k unit vector that points perpendicular to that plane out of the page along the z axis. Okay, it should draw more like this. So we set up a orthogonal system like this, right, where you have an x, a y, and a z, right? X, y, and z coordinates. So if I say minus 750 miles I, right? Since I've defined I to be the x direction to the right along your page, you should all immediately understand what minus 750 I means. It means 750. Remember, the positive I direction is to the right across the page, right?
750 is in the opposite direction of I.
Yeah, to the left, right? So the minus I direction would be to the left. Okay, let me give you another example. Let's say I tell you, all right, a displacement of 3 meters in the j direction. You should understand what that means. That means 3 meters towards the top of your page or towards the top of the board, right? Because we're defining the I direction, positive I is that way, positive j is this way. What if I said 15 meters, minus 15 meters j? That means to the bottom of the page, or bottom of the board, right? Now, here is where it gets super powerful and really cool. What if I said this? I have a displacement that is 2 meters I hat minus 3 meters j. What does that mean? Yeah?
It's basically an xy coordinate, so you're 2 meters closer to like right and then 3 meters down.
So I could actually construct a what here? What could I construct out of this? This is essentially a recipe to build something. Even more specific, like what geometric figure am I building with that? So you said which way?
2 meters right.
2 meters right,
3 down.
3 down. A right triangle, not just any triangle, but a right triangle. And you know how to deal with right triangles, right? Because the summer assignment said you better know how to deal with them. So, what do you do with this? Where is the actual displacement? It's the hypotenuse. This is the actual displacement. So this is a recipe for a displacement. It's saying the displacement is 2 that way and 3 that way. How do you get the actual displacement, the magnitude of it? And what do we call that? Use the Pythagorean theorem, right? A squared plus b squared equals c squared. So this recipe is telling you, hey, you want the magnitude of your displacement? Use those two things and use the Pythagorean theorem. You want the direction? Well, the ratio of those two sides defines the size of that angle. And I can find that angle, right? And I can tell you what that angle is if you want me to. But notice that all of that information is actually encoded here. Okay, let me give you another example so we can understand this a little bit better, even still. So I have a snail, pet snail, and it crawls 50 centimeters east and 250 millimeters north. Okay, so you need to be good at like centi, milli, deci, and kilo, right? You need to be able to convert back and forth between those things kind of easily. Yes? Those are kind of all commonly used prefixes. You don't really have to know like micros and megas and stuff off the top of your head. I mean, those are important, but like not for, you know, quick conversions. So 50 centimeters, 250 millimeters. So how many centimeters is 250 millimeters? 50 centimeters is 500 millimeters. Okay, that's good. Or,
25 centimeters.
okay, so 250 millimeters is 25 centimeters. And 50 centimeters is how many meters? 0.5. And 250 millimeters is how many meters? 0.25, a quarter. Perfect. So if I want to analyze the snail's motion, what should I do first? Draw the diagram, draw the little picture. 50 centimeters and 25 centimeters. So how far did the snail travel? So that's the easy part, right? The distance traveled is just 75 centimeters. But to represent the displacement, I have to draw the hypotenuse. This is the displacement. Now, if I wanted to tell what the displacement is, what's one way to do it? I could get the Pythagorean and do the Pythagorean. If you want the magnitude of the displacement, I have to use the Pythagorean theorem, right? And I want it in meters. So 0.5 meter, 0.25 meter. So I take it, put it in my calculator. Here we go. Ready? Okay, 0.5 squared plus 0.25 squared. And then I want the square root of that. So my calculator says this. 0.0559016994 meters. Does that look good? Did I do it right? Okay, so this is what my calculator said. The calculator clearly is giving me accurate information. However, the answer should not be that. I should be obeying significant digit rules at least reasonably, right? So if I were to apply significant digit rules, this answer should be 0.56. Why only two significant digits?
Let's give them more specific measurement where it's only 3 digits.
Right. My least, input with the least number of significant digits was 2. Therefore, my answer can't have any more significant digits than the least specific input, which was 2. Okay, great. So notice I'm not giving the direction here. I'm just giving the magnitude because that's what they asked me for, right? The magnitude is 0.56 meters. So if I just ask for the displacement, I would argue that 0.56 meters is not the best answer. What's a better way to say it? Well, what's another way to say the displacement that I kind of just showed you guys? Right? So what would that look like? How would I write it out?
50 I have plus 25.
I'm going to do it in meters, but 50 meters.
Plus 25 K.
Okay, perfect. Do you guys understand this IJ notation? It's not really that crazy. It's just saying make a triangle, right? Why is this? I would argue this is a better answer for the displacement than that.
Because it's more accurate, but we determine it.
It's more accurate, right? This is without any rounding or anything. These are exact numbers. That's rounded off. And this one has the angle encoded in it somewhere. That just has the magnitude. If you want to know the direction here, what you're going to have to do, and we're not going to do it right this minute, but you need to determine what that angle is. And you would say something like 0.56 meters at some angle north of east. Get it? So you could either say that, or you could do that. Which one would you rather do? do the first one, right? You could do that, but there's a bunch of extra steps, and it's not as accurate. Okay, I'm gonna take a 5-minute break. Woo-wee. Yeah.
What's the significant digits on that?
Yeah.
Is it? I thought like it was supposed to be only 1 because it was 0.5 times.
Well, the original measurement was 50 centimeters.
Oh.
So that we were kind of assuming that the 0 was significant. You know, it was exactly 50. So it should have been that, and I actually should have asked me, because I should have said 0.50 meters, right? Because if it was 50 centimeters, then it would be precise.
So it wasn't 1 and 2; it was 2 and 3, like the whole 2 measurements. So you had like yeah.
Right. Because the
Yeah,
it said
0.250 and then 0.50.
right. And actually, this is really kind of early in my note building for the course. So later on, you'll see we're actually more careful where we put decimal points in, because if I meant 50 centimeters exactly, there should be a decimal point. It should look like this. Because there's a difference between that and that. That's 1, this is 2. So yeah, no, you're right. I mean, I get what you're It's a fair point. But like I said, you should say this stuff to everybody. That way, we could all fight. Just elaborate. That's it. Fight. Just kidding. No. Yes, I do. Of course I don't like that. No, like I was making a joke earlier with my class. I'm like, okay, so they tell us this first week, just get to know your students. This one kid has, in one of my classes, has like a happy face. I'm like, that is the best. I always want a happy face. Just let you know what? Just keep going. Just keep going. See how bad that is? She sat right in front of me the whole year. No idea what the hell I was. Hi, Mr. Wilson. Okay. Who are you again? Okay, so there's a question about the significant digits of the snail, right? So the question was, shouldn't it have just been one significant digit because it said, because we were using 0.5 meters. But remember the original input was 50 centimeters. So that was 2 digits. We just changed it to 0.5 meters. When I changed it to 0.5 meters, it actually should have said 0.50 meters since we had 2 digits originally. So maybe I'm wrong. Or not. So don't you hate it when you have a teacher who like makes mistakes on purpose or like says things that are dumb and you're like, what's going on? Why did you say that? Yeah, I do that all the time. And they wait for you to fix it. Yeah, I do all the time. So watch out. Also, I actually do make mistakes. Like real mistakes. It happens. A lot of students, they get nervous. They're like, he just like added 5 and 4 and got 10. What the hell is he doing? Did all of a sudden math break? What should happen when I do that is you say, hey, Mr. Wilson, 5 plus 4 is 9. And I'll be like, oh, you're right. I'm sorry. And I'll fix it. It's like, you should not stop me if I make a stupid mistake. Right? You should not be afraid to correct me. Okay. So speed and velocity. Next thing, speed and velocity. Speed is a measure of how distance changes with time. Velocity is a measurement of how displacement changes with time. Really kind of a little bit oversimplified definitions, but not bad. So one of these things is a scalar, and one of these things is a vector. Which is which?
Speed is a scalar and velocity is a vector.
You had physics before, right?
Yeah.
Okay, so stop cheating. We had physics already, so you know. He's showing us that he remembers stuff, and that's cool. Let them struggle for a minute until they're completely lost, and then you can say it. Okay, so speed is a scalar, and velocity is the vector. Hey, S and V. Not that we would need silly little mnemonics like that to remember, right? Right. So when you divide a scalar by a scalar, time is a scalar, by the way. When I divide distance, which is a scalar, by time, which is a scalar, and I really, really hate it when it does that. When I divide distance by time, that's dividing a scalar by a scalar. I can't get a vector out of that, right? There was no direction inherent with either of those two things, so how can I get a direction in the result, right? If I divide displacement by time, displacement has direction. That's a vector. So when I divide it by time, I'm going to get a vector, and that vector will have the same direction as the original one. I don't know where it is. Me neither. Oh, look around. So, is that your book?
Yes.
Is that your book? Yeah. Thank you. Yeah, yeah. So, if something is traveling, if something has a displacement to the east, and you're observing it, then its velocity would be that way. So the displacement is the same direction as the velocity in that case. Okay, same direction. Okay, so we also need to differentiate between instantaneous and average quantities. So let me give you an example to illustrate this. So you take your radar gun out, you go out, you're watching a car drive by, you point your radar gun at it, you push the little button, and the radar gun says 50 miles per hour. What does that mean? What is that? No. I point the radar gun at the car, I click it, it says, yeah, what is that? That's an instantaneous speed. That's saying car speed right this second while you were pointing the finger is 50 miles per hour. Get it? Instantaneous. That's what it is now. Average speed. So let's say you go out for a walk. You go around some circular path that's 10 meters long, and you do it in 5 seconds. Your average speed would be 2 meters per second. Why do I say that's your average speed? Why is that not your instantaneous speed?
Because it's the whole trip instead of just one specific time.
Okay. What else? Why else?
Well, you could be walking for 30 seconds and you sprint for that.
I could have been walking for the first couple seconds, then sprinting. I could have run a little bit, stopped, and started running again. I could have gone a certain distance forward, backwards, and then again, you know what I'm saying? Like, all I know is I went 10 meters in 5 seconds, right? If you're gonna go 10 meters in 5 seconds, that means that on average, you're going to go, I wanna go 10 meters in 5 seconds, and on average, I need to go 2 meters every second, don't I? On average. I don't have to do that every second. I might, I could, it's possible, right? But I don't have to. So it's an average speed. Okay. So let's classify some things as either speeds or velocities. 35 miles per hour east, is that a speed or a velocity?
Velocity.
Okay, because it has, wonderful. How about 0.5 kilometers per second? That's a speed. How about 1.5 yards per millisecond northwest? It's a velocity. Okay, now we're getting involved. 4.6 meters per second. What is that? That's a speed. How about negative 1.2 miles per hour?
Velocity.
Why is that a velocity? Sorry, what?
Because it's going in a negative direction.
Okay, the negative sign is indicating direction. You can't have a speed of negative 1.2 miles per hour unless you're going back in time or something, right? You can't untravel distance and you can't undo time. So you can't have a negative speed, right? A negative velocity simply indicates direction. So now, let's finish this off and then we'll talk about another problem we have. 72 kilometers per microsecond and a big speed at that. Okay, now let me ask you this. And Mr. Goldman and I fight about this all the time. Is negative 20 smaller than negative 10? Yeah?
Yes.
Oh, okay. So in what sense is negative 20 smaller than negative 10? Yeah? Yeah? Okay, so when we say smaller, we mean you're going,
Oh, sorry. What's this?
well, I mean, when you say that negative 20 is less than negative 10, you're talking about that, yeah?
Negative infinity would be the smallest thing possible.
Okay, so you're like defining a number line from negative infinity to positive infinity, and when you go towards negative infinity, you're saying that things are getting smaller, right?
I just feel like smaller can either mean what she was talking about or closest to zero.
Okay, sure.
So maybe in a sense.
Okay.
I feel like it's relative to like the context of it. It was like distance and you talk about velocity. It could be like a longer distance backwards.
Okay.
But,
Okay, so let's say someone comes up to you in the park, right? You're just in Central Park on a nice summer day, and someone says, hey, is negative 20 less than negative 10? What are you going to say? You're going to say yes, right? Because that's the math answer, because they're just presenting you with pure numbers. Now, if some other person comes up to you in the park and says, is negative 20 meters per second smaller than negative 10 meters per second? My answer to that is that question. That question does not make sense. That question is irrelevant. 20 meters per second is faster than 10 meters per second, right? But to ask if negative 20 meters per second as a velocity is less than negative 10 meters per second makes no sense. There's no point to the question because you don't define them along a number line, right? What we're really interested in, if you're talking about that, is which one is going faster, right? And clearly, negative 20 meters per second is faster than negative 10 meters per second, right? So if and when this comes up, he will tell you negative 20 meters per second is a smaller velocity than negative 10 meters per second. And you're going to have to accept it. But I say it's a nonsensical statement. Like, there's no point to making that statement. Right? It's not a small, it's a, negative 20 is a smaller number than negative 10, but talking about it in terms of velocities makes no sense. Right? The velocity may be getting smaller, but it's going faster. So in the physical sense, why would we care? That, see what I'm saying? I don't know if you get what I know what I'm getting at, but okay, some equations. You go to your Regents physics reference table and you'll see this equation. And this equation, next to it, they'll have a guide for the variables and it'll say V stands for velocity or speed, and the little bar means average, right? So V stands for velocity or speed, D stands for distance or displacement. And that's fine enough for Regents classes. But for AP, they use the variable X for position all the time. So a better way to define velocity would be this, or average velocity would be that. Do you understand the difference? Right. Delta X is saying you're changing your position. And if I'm looking at change in position, that is not necessarily distance, right? So you start here at point X, you go to point Y here, and then you go to point Z here, right? Delta X is this. That's your change in position. The distance is this plus this. Right? So if you're calculating speed, you'd want to know that. If you're calculating velocity, you'd want to know that. And they're not the same thing always. So I kind of like having two separate equations for them. There's another way to get average speed. This is a brain buster, right? You're shocked by that equation, aren't you? What does that equation say? Yeah.
Finding the average of the velocity.
Finding the average of two speeds, right? You take the two speeds, you add it together, divide by 2. You only do this with instantaneous speeds. Why do I only do this with instantaneous speeds? Yeah. That could be part of it. Yep.
Because the average is already the average. So why would you be using average speeds to calculate the average?
Okay. But I'll give you an example. Right. You're right. I think where you're going is right. Let me give you an example to explain this a little bit better. So we have 14 people in the classroom, right? Average on the exam is 90%. Okay. Next class comes in, there are 3 people in that class, and they average 80%. Is the average on the exam 85%? How many levels of wrong would it be to say the average on the exam is 85%? Several levels, right? Why? What's one reason why it's really bad?
Because that was the average, the 80% is the average of just 3 people. It's not, taking into consideration just for the whole.
Right? So one was an average for a large group, the other was an average for a small group. And then I averaged two averages of vastly different sized groups and said that was the average. That's dumb, right? It's not just wrong, it's dumb. Yes?
The only way you would be able to get away with that would be if you played in like a ratio.
Perhaps, yeah, you could put it into a, yes, you could weight it like that, yeah. But what should I do if I want the actual average?
Add the number of students and then add the scores.
And you add all the test scores up divided by the number of students, right? Total number of students. So if you look at each individual score and average them, right? You look at instantaneous speeds and average them. You don't average speeds. Why? Well, for one thing, you're not going to get the correct answers. And for another, it's just not right to average averages, right? In my example, did the 85% actually mean anything? I mean, yeah, it was the average of the class averages. But what useful information does that give me? Pretty much nothing, right? It's not useful. Okay, so this we'll illustrate this with this example. And I gotta keep reminding myself to write on a smartboard because I have people watching. I really want to write on a chalkboard. Okay, so you're on a football field, you're at the 30-yard line. 30-yard line. And you run to the 5-yard line. So we probably should define a positive and negative direction here. Which way do you want to call positive and which way do you want to call negative?
Positive 30, like the 30 would be the positive, and moving towards the 5 would make it more negative.
Okay, so we're gonna make towards the top of the page positive and towards the bottom of the page negative. Okay, that makes me happy. You're not trying to like break my brain or anything. So positive is this way, negative is this way. Okay, and then we go to the 40-yard line. And this first one happened in 12.5 seconds, and the second one happened in 70 seconds. You guys all good with my picture? You like my picture? You would have sketched a similar picture, perhaps. Adding the times because, you know, you expect that they're going to be relevant. Two shields. I'm not. I don't know if there's another teacher that's in here that's short. I don't think so. I will. I can ask.
741.
Okay. Whatever. Okay, so we'll call this first one motion 1. And the second one, motion 2. Okay? So what was the distance traveled for motion 1?
Negative.
The distance traveled for motion. Okay. Then you amended it, you said negative. Okay. So is it negative or positive? Remember what the question was. Okay, can distances be negative? They cannot. Distances just get bigger, right? You can't have negative distances. So the distance traveled for motion 1 is 25 yards. The distance traveled for motion 2 35 yards. Okay. Now it says for each motion, what is the displacement from the point where the motion started? So the first one, now we say negative 25 yards. And for the second one, 35 yards. Okay. Okay, so if I write positive 35 yards, right? So if I just wrote 35 yards without positive, would that be wrong?
Yes.
Well, I would say it's not really wrong, right? Because you don't have the negative sign, so by default, you're saying positive. But if you include the positive sign, you're forcing it down the reader's throat that you're talking about a vector and you know you're talking about a vector. So would I mark it wrong if you didn't put the positive sign there? Absolutely not. But if you want to be perfectly clear, the positive sign helps if you want it. So it wouldn't be wrong not to have. Okay, what is the average velocity speed for each motion? So the average speed for the first motion, or the average speed. How do you get the speed? 2 yards per second for the first motion. In terms of speed, how about speed for the second motion? 25 yards per second. What if I was talking about velocity for each of the motions separately? You would have to make the first one negative 2 yards per second to indicate that it was in the negative direction, right? Perfect. Okay, so now here's where we get into trouble. Well, not at first. What's the distance for the whole thing, both motions combined?
60 yards.
Okay. Distance for the whole thing is 60 yards. What is the displacement for the whole thing? Okay, we can force it down our throats by saying plus 10 yards, right? Okay, now, what is the average speed for both motions combined? So what should we definitely not do?
Just do 12.5 plus 70 divided by 2. They're not equal distances.
No, that's not what I mean. Yep. Do not take the average of 2 and 0.5 because those are average speeds, right? So if I take the average of 2 and 0.5, that's 2 and 5, 2.5, 1.25. 1.25 is definitely not the average speed for both motions combined, right? That is where we would be wrong. You would not want to average those two things. So how do I get the average speed for the whole thing?
Add the time and the speeds.
Add the distances and add the times, yes. So the speed for the whole thing would be 60 yards over 82.5 seconds. And I mean, you could find a number if you want, I don't really care, but that is definitely smaller than 1.25. Right? And then the velocity for the whole thing would be okay, how would I calculate the velocity, average velocity for the whole thing? 10 over 82.5. Okay, so this is kind of interesting because honestly, average velocities are pretty much useless. Right? There's not a lot of use for average velocities. Let me give you an example, right? Let's say I start on one side of the desk, I walk completely around the desk and stop in the same point. What was my average velocity? 0. I didn't have an average velocity because I started in the same place. My displacement was 0. My average speed was definitely not 0, right? So what did my average velocity tell me? It told me, well, if you want to start there and end there after some amount of time, you have to go at 0 meters per second to do it, right? The average velocity just tells you, hey, if you want to go from here to there in that amount of time, here's the slowest speed you can go at in a straight line from here to there to do it. That's all it tells you, right? It's not terribly useful information. The average speed is much more useful because it says, hey, if you actually want to travel that amount of distance in that amount of time, you have to go at an average speed of this. Right? So it's much more useful stuff. All right, one last piece, and then we're going to talk about lab stuff. So a cyclist goes 20 kilometers west in 2 hours, 30 kilometers east in 5 hours, 15 kilometers south in 2 hours. What is the cyclist's average speed? I got this. I got it. Don't worry about a thing. I got it. It's all under control. 10 kilometers per hour plus 6 kilometers per hour plus 7.5 per hour over 3. Oh, what? No. He's telling me no. You guys, seriously? He's telling me no. Who's in charge here?
I apologize.
Okay, good. Oh, you want to fight too? Is that it? What? You don't like it? It's wrong. She said it's wrong. Way to hurt my feelings. What's wrong about it? I got average speeds for the 3 intervals and I averaged them. No. Bad. Bad, Mr. Wilson. You don't do that. You don't average speeds, right? This would not get me the right answer. Now, you guys are going to get this wrong. You guys are going to average speeds. You're going to make this mistake. You're going to be going through your practice problems. You're going to have your review packets out. You do these problems and you'll be like, wow, Mr. Wilson's answer is wrong. And then you're going to come to me, you're like, look, the answer key's wrong. And I'm going to look at you and say, you average speeds. And you know what? That's perfectly fine because that's how you learn. You make that mistake while you're practicing and that's how you learn. So if you get into that situation and you're like, wait, the answer key's wrong, what you should do is say, hold on, let me check this. Did I average some average speeds, right? It's a very, very common mistake when you're first starting out. So just be careful of it. So the way you would actually answer this question is how? Over, so something over 9, what is that? 20, 50, 65? 65 kilometers over 9 hours, whatever that is. Right? Not important what it is, just that's the business part. Okay, so let's take out the lab manual. That's enough of that for today. And the people following us at home do not have the lab, nor the lab manual. That is if they are following us. All right, so I should take out the lab manual. Should have had this document open already. Okay. All right, so this is the document we're looking at. So the way we normally do this lab every year is we break into groups, which we're not allowed to do. And we have each group will pick a student to represent the group and be the measuring stick. So then that person will take 5 regular size steps and we'll measure how far those 5 steps are. And then we figure out the person's average number of meters per step. So we're going to do it a little differently this year. we're going to need some volunteers. And judging by how lively and involved this class is, my goodness, I can only imagine how many people are going to jump up and volunteer to do this. She will. You will. Okay. So we need someone to volunteer. You're going to stand on this line and you're going to walk 5 normal steps. Now, be careful, because when I tell students to do this, here's what I've been seeing. So you take 5 normal steps, and I'll see someone go, that's not normal, unless you're like this tall. Or sometimes I'll see people do this. Take them big Frankenstein steps, right? Also, not good. That's not going to help us. You want to just take 5 regular size steps, just like a person, right? Actually kind of backfired on me a little bit, because the first time I did it, like, okay, someone get up and volunteer. And the person was like 6'2". So they took these massive steps. Okay, someone else get up and do it. They were also like hugely tall. And then a girl volunteered, like, oh, it should be good, it should be shorter, that'll bring the average. Oh no, she was like tall too. So right. Who's gonna do it? Okay, go ahead, you first. We need like 5 people to do it. Okay, put your toes on the line and take 5 regular steps. Good, stop there. How big, how far did she go? Where's she at? 177. So that's 200 plus 177. So it's 377, right? Because the first meter stick, this is a 2 meter long stick. Next, go ahead. We need like 4 or 5 people to do this. Okay, how far do you go? Like 111?
115.
115, so 200, 315. Next, come on, more. Go. Okay, good. How far? So you're 10 past the second one. So 410. Okay, perfect. Come on, we need at least 1 more. Come on, do it. Come on, let's go. Okay, stop there. Perfect. Okay, how far? 138, so 338. Okay, we want the average of these values. You don't have to write any of this down yet. We just want the average of those 4 people. Sorry?
360.
360? So that's 360, which is, this is centimeters, which is 3.6 meters per 5 steps. So 3.6 meters. So how many meters is that per step? 0.73 meters per step. Okay, so we're saying that on average, we had 4 people, and the average step length is about 0.73 meters. Now we need to develop another volunteer. Come on, not everybody at once. You know you will. Okay, good. So you need to go out in the hallway. You need to count your steps. Right? So you're going to start in this corner, count how many steps it takes to get to that corner, and then turn and count how many steps it takes to get to the end of the long hallway. So you come back with 2 numbers. Okay, number of steps for the short hallway, number of steps for the long hallway. Okay, we need another volunteer. Perfect. You need to time yourself going through the hallway. So I need to know how long it takes you to go through the short hallway and how long it takes to go down the long hallway. At a nice, steady pace. write down a number is two numbers, yes or no? Okay. So while we're waiting for them, we can talk about them behind their backs. We know about these guys. Don't want to talk. Okay, fine. All right. So we're going to use their data to calculate distances, displacement, speeds, and velocities. What might be that? Yes. Good job for physics. Oh, so you learned all this. Let's talk about windsurfing, race car driving, not NASCAR, not Formula 1. We won't talk about kite surfing. Shouldn't even know this. No kite surfing. Oh, he thinks.
No, I wrote it down.
Okay. All right, so what do we got here?
34 for the short and 55 for the long.
So 34 and 55 steps. And what's our time?
The first one was 1959.
1959.
And was 31.81.
31.81.
Yeah.
Okay. So then you could assume that the other hallways would be 31. Again, when we do this, like every year, we usually just actually do each hallway individually. And you'll find that the long hallways are about the same time as the short hallways, not exactly, but we're just going to make them the same. So 1959. Okay. So from this, we can start calculating some stuff. So if you took a trip from A to B, what distance would that be? Well, we have to convert it, right? Because that's in steps. So how many meters is it from A to B if it's 34 steps? Mm-hmm. Wow.
Oh, wait, no, that's for 5 steps. Never mind.
Okay, so I would just round it like to the nearest meter, so like 25, let's just call it 25 meters. How about the long hallway? It's 55 steps, right? How long is a step? 40 meters, yes. A step is not 40 meters, but the hallway is 40 meters. So we got 40 meters here, 25 meters here, and actually that's about right what we get every year. You guys are right on the money. Okay, so the distance from A to B is, not everybody at once, 25 meters. See, it wasn't that hard. What's the magnitude of the displacement from A to B? 25 meters. I'm not trying to trick you. Now, what's the time from A to B? Okay, so now let's get the speed and velocity from A to B. Just take the speed you want, the distance over the time, right? So, what's the average speed from A to B? .27? No. Let's say 1.3. Okay, let's not get too crazy. Let's say 1.3. How about the average magnitude of the velocity? Same thing, isn't it? Okay. All right, so we're going to continue this. You guys will be continuing this on Monday in class.
May I have your attention?
7 Green will be continuing this virtually on Monday. I think they were a little farther along than you guys, but not too far off. We're pretty close. So you guys, may have to wait a minute or two for you guys to catch up. That doesn't matter anyway. When we start on Monday, we're starting with do now number 2. In the meantime, we're not working on this lab while you're home, but that doesn't mean that you have no physics to do. There's plenty of physics you can do if you want. Thank you, Ms. Rose. You're welcome. Thank you. Have a fantastic weekend. And if you don't, it's probably your fault.
Bye.
Thank you, Mr. President.
That's right.